Okay, so today we're going to be discussing E1 and E2 reactions. So there is definitely a lot to know when it comes to these reactions, so I'm just going to make it pretty quick. So I made a video about SN1, SN2. Those are substitution reactions. E1 and E2 are elimination reactions. So let's just draw out what that looks like. So say something looks like this. And then we have bromine here. Let's have it react with NaOH. I'm just going to get rid of those. The major product would look something like this. So we would get rid of the leaving group. As we know, the bromine would be a good leaving group, and we would get left with a double bond here. So that would be the major product. So essentially, the leaving group leaves, and then this, which acts as a strong base, takes the hydrogen here from one of these carbons. I'm just going to do this one here. The carbon here, or not the carbon, the hydrogen here is plucked by the strong base, and the leftover electrons go from the covalent bond to the pi bond, forming the double bonded alkene. So that is essentially what an elimination reaction looks like, but as we know, there is a lot more to it than just that. So first, let's talk about E1 and E2 and what the difference is. So like SN1 and SN2, E1 is a two-step process and E2 is a one-step process, which does seem a little confusing because E1 you'd assume is one step, but nope, it's the other way around. So this, what I just drew here, this example would be an E2 reaction because it happened in one step. So let's pull up the handy reaction chart so we can think. So you in the future would be able to solve this problem. So we have NaOH, which OH here is NaOH since the ionic bond would break, and we would have the negative charge OH. So NaOH, we know we have that. Oh, sorry, didn't mean to get rid of that. We know we have OH, and we have a tertiary leaving group because bromine is attached to a carbon, which is attached to 1, 2, 3 other carbons, major constituents. So it is a tertiary substrate type. So that would leave us with only E2. So there wouldn't even be SN1 to begin with. So we talked about that. That is how this type of mechanism would work. So how would this work, where we have the strong base with the weak nucleophile? So OH is a strong base and a strong nucleophile, but how would it work if it was a strong base without a strong nucleophile? So let us just draw another example here. So we have this, and let's have bromine once again. Actually, let's have another carbon there. And my go-to example for this would be tert butoxide. So it would essentially look like, or it'd be Na or K also. So essentially, what does this look like? It looks like this. So this is tert butoxide. Has a negative charge, and the reason why tert butoxide is a strong nucleophile, or I mean a strong base but not a good nucleophile, is because we know it is missing a covalent bond here. It only has one covalent bond. It has 3 groups of lone pairs and a negative charge. So it is a good base. It wants to take hydrogens away from something. It wants to grab some hydrogens, or it look like that actually. It wants to take hydrogens, but it is not a good nucleophile because it is considered a bulky base. So if you think of something like OH is, if you just think of it physically, it's pretty small. It's just 2 elements. It's not that big or anything. But tert butoxide looks like this. It has 4 carbons and an oxygen. So it really can't participate in any SN2 reactions because tert butoxide is way too big to essentially jump in. Say bromine leaves, tert butoxide is way too big due to steric hindrance to go in there and replace it via nucleophilic attack. so it doesn't act as a nucleophile. The steric hindrance from this tert-butyl group prevents it from being a nucleophile. So it can only act as a strong base. So let's draw out how does it operate? How does this work now? Because it will not make the, I've always pronounced this wrong. Oh, excuse me. I've always pronounced this wrong. Anti-Markovnikov. I'm just going to say anti-M reaction. So I'm going to back up a little bit. This would have an anti-Mark reaction. This would have, so I'm going back to edit this. In the video, I call it this Russian word. It is actually not. It is called the Zaitsev product. In the video, I'm going to call it a Mark product. It's actually a Zaitsev product. And the anti-Mark product is actually called the Hoffman product. Please excuse my mistake. So just to clarify, when it looks like this, when it's a more substituted alkene, this is a Zaitsev elimination product. And when it's the less substituted alkene, it is the Hoffman product. It is not Markovnikov. That is actually in OChem 2, and we do not need to worry about that yet. Please excuse my mistake. It would look like this. That would be the reaction with tert butoxide. So, in this, these are both E2 reactions, but when using a good nucleophile, good base, we get the Mark reaction where it is a tri-substituted alkene, but in this, it is only a di-substituted alkene. So I'm just going to that and that. I'm just going to, like 3, it's tri-substituted. This one is di-substituted. So you may think, well, why does it do the anti-Mark reaction? Why does it do a di-substitute alkene when it could have been here, or the pi bond could have gone here and it would have been tri-substituted? How does that make any sense? So essentially, as I said earlier, tert butoxide is a very bulky base. So I am just going to draw out the mechanism here. So it is a bulky base. So it would look like this. So the leaving group, bromine, it's leaving. So tert butoxide is thinking to itself, well, where is the easiest hydrogen I can grab in order to, since we take this hydrogen to make the double bond, this says, the tert butoxide says, I want to get a hydrogen, but these hydrogens here, and these are the available hydrogens. So we have the solo methyl group, and then the carbons that are on the cyclopentane. So we either have this, the 1 group, or the 2 group. That wasn't a 2, there we go. So it says I can either take it from, I can take this hydrogen here, or I can take it here. Right here. And normally, if it was just OH, it would take from here. It would say, I want this hydrogen, I'm taking that to make a more stable product, the Mark product. But it does not do that because it's so bulky due to the steric hindrance, it really can't find a way to get in there without interacting with all these groups here, or that methyl group there. So it has to settle by taking a methyl group from here. It says, you know what, I'll take this hydrogen, it's easier, it's the only one I can get, I'm going to take what I can get. And then the hydrogens from the covalent bond with the hydrogen goes to form a pi bond, leaving us with the anti-Mark product. The anti-Mark product with a sterically hindered strong base. So what I just drew would be this, where we have a bulky base that is a weak nucleophile. So that is how, actually, there's one more thing I need to talk about with E2. So say we have a case like this. Ooh, that wasn't right. Say we have the bromine here, but now it's on a wedge. We're going to be talking about stereochemistry here. So this is just a wedge, and then we have, oh, excuse me, we have methyl group. Actually, I'm just gonna do CH3 to make it easier. CH3 methyl group, and then a methyl group here. So in E2 reactions, there's something called, I'm gonna write this out because it's very important. Okay, I don't know why that's so tiny. Anti-periplanar. So essentially, we're doing a reaction where it's OH, good nucleophile, good base. It is ready to. Actually, I'm just gonna draw a carbon here. Actually, no, I'm not gonna do that. We have a good base, good nucleophile. We're gonna be doing E2 right here. But you might be thinking, well, hold on. Which carbon, the one on the wedge or the one on the dash, which one's gonna have the pi bond? Actually, let's just draw, just so we can indicate that this is not a mirrored compound. Let's do another methyl group here that we can just kind of ignore. So you might be thinking, well, which methyl group, is it this one or is it this one that's gonna react? So we know here we would have hydrogen on a wedge, or a dash, sorry, hydrogen on a dash, and then another hydrogen on a wedge that we are just gonna draw. So essentially, the leaving group, bromine, must be anti-periplanar to the adjacent hydrogens that are going to be leaving to form the reaction product. So bromine must be on a wedge. If bromine's on a wedge, the one it will react with will be on a dash. So let's just draw what the product will look like. So this would be the product of that reaction. And the reason why I can draw it out in the chair flip conformation, actually I should have drawn it as hexane if we want to do that, but essentially let's do a, let's think about how to draw this. Basically, if we had, this is an example here, if we had a Newman projection, so if we had bromine here, hydrogen must be here, must be anti-periplanar in order to form the product. So that is all the ins and outs of E2. So now let's finally talk about E1, which is a little easier to understand. So let's do another similar starting molecule, and we're gonna have bromine. Once again, this time we are gonna be reacting with a poor nucleophile, a poor base, H2O. So in this case, we can assume if it's E1, it's going to be two steps, as we said. Bromine's going to leave, and now there's going to be intermediate that is going to be looking like this. So the intermediate has positive charge there, but we're going to be doing a 1,2 hydride shift, so hydrogen will go here to make a more stable carbocation. So that's where it's going to be right there. And then eventually H2O find its way in there. And eventually that hydrogen is going to leave. Oh, hold on. I am drawing SN1. Please excuse me for a second. H2O. We'll take the hydrogens here. giving us a similar looking product as before that looks like that, which is the Mark product. So I hope this video shed a little bit of light on E1 and E2. I know I did not go into everything. I'm going to do some more practice problems at some point that I'm going to be posting on this channel. Please give me some slack here. I am still an undergrad student, so I do not know everything. Please correct me if I got anything wrong, and I'll see you in the next video.